First of all, thank you for this glorious introduction. At the beginning, I want to congratulate you for this initiative to organize such a very, to say, appropriate and helpful event for the young researcher, I mean PhD students. And at the end, I want to thank you very much, to express my gratitude for inviting me to present a keynote lecture within this event. I selected for this presentation to show, by means of an example, how much is important testing in the field of our profession. That's why the title is Experiment Assisted Design and Research of Steel Structure for Seismic Areas. Sometimes structures, not only steel, even prestressed concrete structures could be difficult. They could be too complicated to be designed or studied only based on simple code formulas or theoretical methods. Their shape is complicated, the loading conditions are complicated, the material properties could be difficult to model, there are difficulty to model and characterize the answer, the response of these structures under complex loading conditions, difficult to model and characterize the essential parameters, I mean capacity, stiffness, ductility, and sometimes even difficult to estimate the safety margin. If we are looking, for instance, to seismic resistant structures, the actual trends in this field can be, if you want, aligned on three directions. One is referred to the characterization of seismic action, which still remain a big interrogation. Another one is to characterize or control the structural response, and a big attention is related to new structural system, devices and materials. All of this, but particularly the last directions, is the one which needs almost in all situations for testing. Modern design codes like Eurocode package have special sections related to the application of testing as a base of design. In this case is Eurocode 0, 1990, in the Annex D, which offer a framework, offer the principles how to plan, to organize, to realize, at the end, to use the results of testing. This is the summary of this annex, and here you have some details related to the types of tests which are covered by the general provisions of the code and the planning of the test. But there are also specialized codes dealing again with test-based investigation, either to use in developing new solution or as a base of design. And one of these, because we are speaking about seismic, is the Euronorm 15129, which deals with anti-seismic devices. For simple anti-seismic devices, if you want dissipative braces or dissipative links in eccentric braces, still much more sophisticated to active system, including tuned mass dampers and others. There are in this code provisions for material testing, for validation of a given device, for factory production control, for calibration numerical test, and at least, but very important, conformity test to be done on the site when the devices are coming there to check if they are conform with the design. I will show to you a case study, a very interesting project. We dealt with this in this very spring, related to a new solution, at least in Romania, applied for a high-rise building in Bucharest, which which refers to frame buildings with closely spaced columns connected together with coupling beams, short beams, which these beams are in fact the source of ductility, and at the end the system leading to the dissipation of the energy induced by workspace. The problem in this case, the problem in the case is due to the fact these beams are short. Some of them are outside of the provisions. In the sense, the contribution of the shear force becomes really important, and the classical model based on using plastic hinge model in the global analysis cannot be applied in a classical way, because you have to account for the interaction between shear force and bending moment. So this is the problem we investigated, and even the designer, in order to try to, if you want to give more possibility and to control the appearance of the plastic hinge, he provided a reduction of the cross section of the beam using the so-called dog bone solution. Even in this case, for short beams, you will see where necessary some intervention and some correction of the initial design in order to make them working properly. This is a short description of the main characteristics of the beam, of the structure. You see, it's a nearly 100-meter high structure in Bucharest, 18 story, and there are two framings. Is the core one and the perimetral one, which are composing a kind of tube-in-tube structure, working like this by means of this coupling beams. This is the structure. You have here the main dimensions of the beams. Some of them are really short, as you can see. And you have the scheme of this beam. The columns are cross, double-T cross sections of those columns. The beams are T-beams, IPE beams. And in order to make easy the transport and direction, the designer also imaginated to have this splice, the idea being to transport the columns with half of the beam already installed, and to connect by means of this splice. This was also a matter of concern, and it was the subject of our investigation. Preliminary finite element analysis was done in order to try to have some more information before testing about the answer, the response of the structure under cyclic action. After it was the test, you see, with a full-scale test for a very huge sub-assembly of the frame. Again, the numerical model under calibration now based on the test results, and with the already calibrated model, the numerical study on the aim of optimization the solution. So you have again the dimensions of the beams and the geometry of the dog bone, and in pink you have the specimens which have been tested in our laboratory. This is the numerical model with the initial solution including also some stiffeners on the web of the beam and some stiffness of the web of the column. From this phase we practically found that those stiffeners have to be eliminated, and also from this phase first correction of the dog bone geometry was applied, because you will see at the end another one was necessary after testing. This is the testing setup, the model and image in laboratory, and because he's a young colleague here, you can imagine and calibrate the dimension of these specimens. Have been tested, as was marked in the table, two types of specimen, including two different lengths for the coupling beam, a long one and a short one. 3 tests, cyclic tests, have been done in both these cases. So this is the image, and now you will see some view during the test. This is the first, for the first long specimen. The plastic hinge forms in the dog bone area, as you can see, but on the other hand, something unexpected. It's a failure in the weld, in the affected zone. Practically, it had no happen because this is the role of the dog bone to protect the connection, but it was happened due to some flaws in the welding. You have here the details of this, and at least in this case, no problem with the splice. This is the second specimen, long specimen, quite similar. In this case, some lateral torsion effects have been observed, but in practice will be the slab which probably will arrive to prevent, but anyway it's a matter of concern and have to be carefully realized the practical solution in design in order to avoid this. Again, no problem in the splice, and the third long specimen, and again with failure, brittle failure in the heat affected zone, also something which is not proper and which cannot be accepted. Now, the short specimen. In fact, this is the case where the contribution of the shear force is outside of the limits accepted by the code. The failure is in dog bone, again lateral torsion, but at the end the failure is happening just there where have to happen, but in this case some sliding in the middle splice was observed, and the problem of this sliding is it induced some eccentricity and could be dangerous because change the stress state in the beam, and again had to be avoided. It is now the second specimen, quite similar, the same type of observation, but even in this case we can observe the crack initiation in the heat affected zone, also something which is a bad signal. So the last one, in this case it's okay except the sliding in the middle splice. You can see the cycles for the short specimens. They are pretty good dissipative capacity, and now the numerical model was calibrated via these test results, and you can see in red the numerical model compared with the experimental cycles. They are fitting really very well, and it enables to us now to modify the geometry of the dog bone in such a way to reduce the stress concentration in the region of the welding, to reduce enough in order to avoid for the future application to have crack initiation in these areas. So, this is the two situations. This is before and after. Now, practically the major concentration of the stresses is in dog bone, as in fact desired when apply such a solution. Some concluding remarks after this study. The first, and this is very positive, this reduces beam section coupling beams proved excellent ductility and rotation capacity up to 60 milliradians before starting initiation of the failure. The plastic rotation capacity has two major components: the rotation of the beam in the dog bone area, accompanied by the distortion of the web panel in the reduced region. And for shorter beams, the interaction shear bending is recommended to be considered in the model in order to have a good control of the phenomenon. Could be problems by flange cutouts, because in case of some flaws, premature failure could be initiated due to the low cycle fatigue effects, and for this reason always it's necessary to be performed non-destructive control of these cuttings. Flush end plate beam splice connection due to sliding might cause brittle failure due to the bolt fracture, and it's not at all recommended. Better is to avoid splice and connect coupling beams to the columns on the side. Finally, the numerical model was validated, and it was proved to being able to predict with a good accuracy the response of the structure, and consequently it can be used to analyze and optimize all the coupling beams, not only the one which have been tested. And to conclude at the end, laboratory tests full or at reduced scale enable to understand the real behavior of a structure, component, detail, and offer a realistic base to validate a technical solution or develop engineering calculation models. Numerical models, if properly calibrated by test, can extend the experimental database by so-called numerical testing. And without the experimental calibration, numerical models alone cannot replace the test. And this is our team. Thank you very much for your attention.